Hello, A-level students, and a warm welcome to an exciting journey into the world of vectors brought to you by International Online School. Before delving into the intricacies of this captivating topic, let's establish a solid foundation by familiarizing ourselves with key terms that will guide us through the fascinating realm of vectors. The first thing we must understand before starting the topic vector is physical quantities. In the realm of physics, we encounter various quantities, broadly classified into scalars and vectors. Scalars, such as distance and temperature, are characterized solely by magnitude, numerical values without direction. Vectors, our stars for today, boast both magnitude and direction, adding a dynamic aspect to their characterization. Let's understand both to better understand our today's topic, vector. The second thing to grip the topic vector is magnitude and direction. Magnitude represents the size or numerical value. Think of it as the strength of a force or the speed of an object. Direction, on the other hand, adds a crucial spatial dimension to our vectors. Envision an arrow pointing north. The arrow's length signifies the magnitude, and the direction is, quite literally, north. Combining these elements equips us to fully grasp the essence of vectors. Let's understand them by examples. To solidify these concepts, let's consider a car. If it's moving at 60 km per hour, we are dealing with speed, only magnitude. Now, if the car is also moving east at 60 km per hour, we transition to velocity, a vector with both magnitude and direction. Force provides another example. If a force of 20 newtons is applied at an angle of 30 degrees above the horizontal, we are dealing with a force vector. The magnitude is 20 n, and the direction is 30 degrees above the horizontal. Comparison of vectors and scalars can give us a detailed overview. Let's picture a journey. If we are merely measuring the distance covered, that's a scalar quantity. But if we consider both the distance and the direction from the starting point, we are dealing with a vector. Scalars are the magnitude, while vectors, with their directional prowess, bring a richer perspective to the table. Let's discuss another example to clearly understand the difference between vector and scalar quantities. Consider a ship navigating the vast ocean. If we measure the distance it travels from its starting point, we are dealing with a scalar quantity, specifically, the distance covered. Now, let's elevate our perspective. If we not only measure how far the ship has traveled but also take into account the direction it is moving, we are dealing with a vector quantity. In this case, the ship's velocity becomes a vector, encompassing both magnitude and direction. For instance, if the ship travels at a speed of 20 knots, a scalar value, and it is moving northeast, a specific direction, we now have a velocity vector. The magnitude is the speed, 20 knots, and the direction is northeast. This comparison highlights the distinction between scalars and vectors. While scalars only have magnitude, vectors add the crucial dimension of direction, providing a more comprehensive description of the ship's motion in the boundless expanse of the ocean. Now, let's shift our focus to vectors and unravel their complexities step by step. Types of vectors. Vectors, the versatile entities in the realm of physics, encompass a spectrum of types, each tailored to fulfill specific roles. Among them are displacement vectors, which delineate the change in position of an object from its initial to final location. Velocity vectors encapsulate not only speed but also the direction of motion, crucial for comprehending dynamic systems. Force vectors, another integral category, embody the influence capable of altering an object's state of rest or motion. These vectors, akin to specialized tools in a physicist's toolkit, contribute to a comprehensive understanding of physical phenomena. By distinguishing between these vector types, physicists navigate the intricacies of spatial relationships, motion dynamics, and the forces that shape our physical world. Let's study the parts of vectors. The concept of the parts of vectors involves dissecting these entities into components. In the context of a two-dimensional, 2D, space, vectors exhibit two fundamental components, horizontal and vertical. These components serve as the foundational elements that, when aggregated, constitute the complete vector. Imagine the horizontal component as the vector's projection onto the x-axis and the vertical component as its projection onto the y-axis. By deconstructing vectors into these constituent parts, mathematicians and physicists gain a nuanced understanding of the directional aspects inherent in vector quantities, facilitating precise analysis and computations in various scientific disciplines. The next thing is representation of vectors, theoretical and graphical. The representation of vectors involves two approaches, theoretical and graphical. Theoretical representation employs mathematical notation to express vectors, typically denoted by ordered pairs or column matrices. On the other hand, graphical representation utilizes arrows, where the tail of the arrow signifies the vector's initial point. The length of the arrow corresponds to the magnitude of the vector, and the direction in which the arrow points indicates the vector's orientation. This graphical depiction offers a visual understanding of vectors, making it easier to grasp their magnitude and direction. Both theoretical and graphical representations are valuable tools in comprehending and working with vectors across various mathematical and scientific applications. In our next installment, we'll delve deeper into vector operations and applications, unraveling the mathematical intricacies and practical significance of these dynamic entities. So, stay tuned, embrace the vectors, and let the journey continue.